Good afternoon, everyone. First of all, I want to thank everyone for putting their time and being here for my presentation. I'm honored to present my work from the past few years, which was about nonlinear estimation and control with application to upstream processes. First, I'm gonna give you a little bit introduction and background about the work and talk about the importance of that. And then we'll talk about control and estimation system that we use for this project. And then we'll go over two case studies that we had about advanced deep water monitoring and system and managed pressure drilling automation. And then we'll talk about the contributions of this work, and in the end we'll conclude the presentation. So extracting oil is becoming more and more challenging with tighter formation and harsher environment. So as the over the years, as the drilling reservoirs gets depleted, so the drilling companies go and have to go and drill in harsher environments and tighter formations. Like in these graphs, you can see the shale rock and also the tension leg platform. So with going to the problem with going to harsher environments and tighter formation is the drilling cost. So this one increases the drilling cost significantly. And another problem is the safety that needs to be improved. So the companies, the upstream company is the most dangerous industry, oil and gas industry. So there is really a need to attenuate abnormal conditions with preventive versus reactive approach. So in this picture you can see the pictures of some of the big catastrophic events that happened in the past. The first one, Deepwater Horizon in 2010, and then Sonderhorst platform in 2005. So these events lead to environmental costs, and also that they threaten the safety of the operators and also increase the costs. So what can be a solution for these upstream challenges? So one of the challenges that upstream processes are mainly manual. So the companies in upstream, they say, okay, we can design. The other industry, for example, the robot industry, design automated robots, and the UAV industry design UAV, but we cannot do automation in upstream. So, but the other problem for upstream is that even if they want to design a controller, there is still a lack of a sensor and high-speed communication system. So, but recently, new kind of data transmission and sensors have been introduced to this industry. So these can help in filling the gap, and therefore we can design controller based on that. So the goal of this project is coupling of high-speed communication network with control systems. So for this, two case studies are investigated. Managed pressure drilling and tension leg platform balancing. And to do this, we use MPC, which is model predictive control, and moving horizon estimation in designing the control system. Okay, so I'm going to talk about the control and estimation that we have used in this project. So for controller, we use model predictive controller. How model predictive controller works is that it predicts the system behavior in a time horizon in future. For it, it gets the system model and creates a cost function based on that, and tries to optimize the cost function in that prediction horizon, and based on that it determines the best values for manipulated variables, so that our control variable can reach to the reference trajectory, and then only implements the first input, and then the next cycle it again gets the data and implements it over the next prediction horizon. So this cost function that you can see here is a squared error term, like especially because of the squared error between the control and the controlled variable and the reference trajectory. So but there is another new technique for the error term, which we call L1 norm with deadband. It's basically absolute error, but because it's not differentiable, we add select variables to make it differentiable, and then we add select variable for set point high and set point low, and this way we put a deadband around the set point, and we believe this approach can increase the robustness of control systems. And also it is with this approach the control can react better against outliers, noise and drifts, which is commonly seen in industrial processes. So in this graph we just theoretically show you how they would react, how we think they would react in different conditions. So for example, a squared error, when there is a outlier, noise and drift, we expect that controller action will change based on those. But L1 norm with deadband, as you can see in this graph, it should be more conservative about it. So moving horizon estimation. For estimation, we use moving horizon estimation approach. So it's very similar to model predictive controller, but it looks past in time. So it looks past in a time horizon, and again it gets the system model and creates the cost function. The cost function is the difference between the measured variable and the modeled variable, and it does optimization and tries to estimate the best value for the estimated variables, so that all of these measured values get closer to the all of the estimated variables get closer to the measured variable in the past time horizon. Again, the cost function that you can see here is a square error because of the square error term here. We just the same as the control part, we can also have L1 norm, which is a new technique, L1 norm with deadband. And again, we expect that this can improve the system smoothness and make it continuously differentiable. And it should be less sensitive to the corrupted data for industry. So this graph here shows the overview, schematic overview of our controller approach. So the measured variables, after getting measured variables, the model of the system that we give to the controller or estimator is given to orthogonal collocator. I don't go detail about orthogonal collocator because it's a common technique in control. And in orthogonal collocator, the differential algebraic equation are changed into polynomial equations, and they are then fed to the controller and estimator, which does the calculation of that and prepares the cost function and gives it to dynamic optimizer, and then gets the result from dynamic optimizer, and based on that determines the manipulated variable and estimate variable and gives it back to the process. For dynamic optimizer, we either use active set method or interior point optimization method. Both of them are derivative based approaches. Okay, as I mentioned, we did 2 case studies for the coupling of high-speed communication with advanced controllers. The first one is advanced deep water monitoring system, which was a smaller part of my project. So first of all, the goal of this project is to design a controller and a monitoring system to balance TLP, tension leg platforms. First, what is a tension leg platform? Tension leg platform is a vertically moored floating structure in the ocean, and it is a house for drilling and production equipment. So there has been no research in the past regarding balancing TLPs using the ballast tanks. But what we see is that TLP platform control is very similar to UAV control during hovering. So a quadcopter is controlled by manipulating thrust forces from individual rotors as well as balancing drag torque, and TLP is controlled by manipulating the ballast tank water levels as well as tendon lengths. So the goal here is to design a monitoring system for the TLP platform and then design a control system based on that. And in order to do that, a high-speed sensing and communication system is required. So in this slide, I go over the monitoring system that we designed. The monitoring system for TLP is based on fiber Bragg grating sensors. How fiber Bragg grating sensor works is that wavelengths is sent through laser to the Bragg grating sensor, and then the Bragg grating has different refractive indexes, and based on that it reflects back part of the wavelengths, and we get that wavelength, and based on its value we can determine the temperature and the strain values. So this picture shows the schematic overview of the monitoring system that we designed, and you can see it's a combination of multiple programming languages that can talk to each other. To install them on TLP tendons, we used specially designed clamps on each one of the tendons, as you can see in this picture. Results after installation. So we actually installed this system on two real tension legs on west coast of Africa, and you can see the real results from that. And you can see that in 24 hours we have two tides that happen over time, and you can also see the waves, the smaller noises here. So this system showed that it is much more sensitive to any change in the environment. For example, storm from in front impact, and also boat docking was very visible on this system. So the operators, their conventional system couldn't catch this. So for designing the control system model part, what we said in each one of the tendon, the load is a load of the platform itself plus the load from the tank, and minus the buoyancy load, and minus the wave load, and minus the tide load. Then for load of each tank, we just use the time transient equation for the volume of the tank, which is dependent on the pump flow rate and the exit flow rate and exit valve opening. For buoyancy, we just use an empirical equation to determine buoyancy in the modeling part, but for controller, we just say buoyancy is measured. How it is measured is that it's the percentage of the platform that is inside water. For wave and the tide actions, we modeled it with sinusoidal equations, but for the controller, they are assumed to be disturbances. So this graph shows the schematic overview of the control system. As you can see, the tide and wave actions are considered as disturbances into the system, and the data acquisition sends the measurements to the controller, and the controller also gets the set point from the operator. So for modeling the TLP platform itself, we use the equation that we just showed you, and also we use the same ones for the controller design, except for the tide and wave and the buoyancy. So these are the results of the control system in just a simulated environment. As you can see from these graphs, that the dashed red line shows the change in the loads over 24 period without controller, but the other lines show how that load changes with controller. You can see that the controller is able to significantly decrease the tide and tide effect on the TLPs. So this controller was mainly designed to attenuate the effect of tide, not the waves. So whenever the tide is falling, the controller opens the valve so that to compensate for that, and whenever the tide is rising, the controller opens the pump to compensate for that. And we designed the controller so it either opens the pump or opens the valve based on the magnitude that it requires it to. And also in the graph on the right, you can see that how the volume of the tank is changing based on what the controller wants. So we believe that with these ones we can say that automatic balancing can result in reduced drilling time, because the TLP becomes more balanced, and also this can lead into increasing the lifetime of the TLP. And also advanced monitoring and control system can improve the safety of the TLPs for sure. So the next section, which is the majority of my project, is the managed pressure drilling automation. First of all, what is a managed pressure drilling? So in managed pressure drilling, mud is pumped with the main mud pump, and it goes through drill string and goes through drill bit and comes backward up to in the annulus and goes through the chuck valve into the mud pit. And weight on the bead and rotation speed are used to change the rate of penetration of the bead, and also main pump and the chuck valve are used to determine the pressure here, with also hydrostatic effect of the mud. Sometimes gas influx happens, and if it is more than a specific value that cannot be controlled, we call it a kick. Some of the variables are known, that from known we mean we can measure them. They are everything in surface, but from the variables at the downhole we can measure RPM and weight on the bead at the downhole, because RPM and weight on the bead are different from surface and the downhole. And also annulus pressure is measured, but we can send it to the surface through either mud pulsing or wired pipe technology. Not every variable can be measured. Some of them are unknown, and that is the density in the annulus and also friction factor in the annulus. And downhole drilling fluid and also gas influx flow rates, they cannot be measured. So as we mentioned, for this project we designed a controller based on wired drill pipe. So as you can see in this video, so the measurements go through a wire line in each of the drill pipes, and at the end of each drill pipe, in each connection, it goes through a coil and then that gets connected to the next drill pipe. In this way, all of the pressure measurements are sent to the surface, and this is a new technique in the upstream industry that has very high speed. Okay, so first we want to talk about the previous work that has been done for managed pressure drilling. So in managed pressure drilling, the researchers have looked at it as two separate tasks. So part of the researchers have tried to maximize rate of penetration with optimization techniques with changing the RPM and weight on the bead, and some of the researchers have tried to regulate borehole pressure with changing the chuck valve and the pump flow rate. So the thing is that ROP also depends on borehole pressure, and borehole pressure depends on friction factor, and through friction factor it depends on the RPM. So we believe that with this controller, for the ones that have designed the ROP system, if they consider these as two separate tasks, they ignore the effect of weight on the bead and RPM along the drill string, and also they have ignored the effect of downhole pressure on the rate of penetration, and there is a potential for improving that. And for the pressure, and most of the researchers have used surface measurement without wire drill pipe, and this can lead to delayed response to the kick event, because whenever a kick happens at the downhole area, it takes some time for the effect of kick to be felt at the surface. And also estimation of the fluid properties becomes difficult with this, because we are not measuring pressure, and this leads to reactive pressure control versus proactive. So, and also most of the works have been done with linear controllers, and this system can lead to decreased and more variable ROP. So the question is it possible to design a comprehensive controller which considers both of the tasks simultaneously, and what will be the advantage of that? So our proposed solution is a comprehensive controller that controls both of the tasks simultaneously. So it tries to control both borehole pressure and rate of penetration at the same time, with changing all of the manipulated variables, including chuck valve opening, pump flow rate, RPM, and weight on the bead. And the features of this controller: first, as I mentioned, it simultaneously controls both of the variables, and it also again, if we want to have such kind of controller, we have to consider the interaction between drill string and the hydraulics. And also we can propose a new methodology for kick attenuation based on direct borehole pressure measurements from wire drill pipe telemetry. And designing, and also another thing that we wanted to do is designing multivariate controller using multiple sensor measurement along the angles. That this is possible with using wire drill pipe. What are the expected advantages? Expected advantages are higher ROP and less fluctuations in ROP, improved kick attenuation with adding extra manipulated variable, because we add extra load and we can further increase the pressure in the angulus, and we can decrease the gas influx flow rate faster. And also this can lead to earlier detection of cuttings buildup during drilling, and in the end it will improve the safety and reduce the drilling cost. So model components that we use, I just go through them as an overview. For pressure hydraulics, we use the lower order model and from Stamnes et al. And then, as I mentioned before, the interaction between drill string and hydraulics needs to be considered so that we can have a comprehensive controller. For that, we say ROP also depends on the downhole pressure. Therefore, we use Brigham Young model, which has a term for the downhole pressure effect on ROP. And we also say the friction factor in the angulus depends on both axillary and rotational flow of the mud. So as you can see in this graph, mud has two kinds of flow rates, axial flow rates and rotational flow rates. So there are some empirical equations relating the friction factor in both of these flow rates. So we use this, and we said, okay, if we change the rotation speed of the drill string, we can affect on the rotational flow of the mud, and therefore we can affect on the friction factor, and we can affect on the pressure loss. And this way we can affect on pressure with changing the drill string characteristics. So this is one of another contribution that has been done before and is the unique thing for this controller. And to model the drill string dynamics, for the drill string we use multiple mass spring damper pendulums in series, and for the weight on the beat dynamics we use first order price dead time model, which is an empirical model. And both of these relate the surface value for weight on the beat to the downhole weight on the beat. And another thing for this research is that previous researchers have only considered one weight on the beat, while this research considers both surface and downhole weight on the beat, and the same thing also for RP. So how we design the control system? First, we put the pressure controller, and it controls the downhole pressure with changing the pump and the valve, the chuck valve. Then, because this is a model predictive controller and it needs a model of the system, not every variable is measured in this controller. So therefore, we need to have estimator, as I mentioned before, so that it can estimate some of the values for some of the variables, for example, density, friction factor, and gas influx. And it is fed to the controller. And therefore, and after that, we added ROP optimizer with the interaction between the drill string and the hydraulics. And this ROP optimizer is able, to determine the best manipulated variable by considering both of the dynamics of the drill string and the hydraulics. And it determines the chuck valve air opening and the pump flow rate. And at the same time, it also determines the best downhole weight on the beat and RPM. So again, we have two different controllers, one for weight on the beat and one for RPM, which each of them get the set point from the comprehensive controller, and then they change the surface values for RPM and weight on the beat so that the downhole values for them can get closer to the set point ones. So this system, during normal drilling condition, this system, the ROP set point is given to that, and based on that, it determines what is the downhole pressure set point based on that, and based on all of the interactions within the between the drill string and the hydraulics, and based on that it changes all of the variables in a way that it can lead to higher ROP. And for kick attenuation, we also proposed a new methodology for kick attenuation, and it is this way that during normal operation we have our set point as downhole pressure. Whenever a gas influx happens, at that time the value for the pressure at the downhole that is measured with the wire drill pipe is going to change. If it is more than a specific limit, then the controller is going to say, okay, we have a kick condition. And another way for the controller to determine if a kick happens is that the gas influx flow rate increases. It gets the gas influx flow rate from an estimator. So, okay, first it determines a kick happen, and what it does is that it switches the controlled variable from downhole to the surface and sets the chuck valve pressure as a new set point. And its new set point is the value of the chuck valve before kick happen plus an error term, which is like a PID equation. So then it tries to change chuck valve opening and the pump flow rate, and at this also rotation speed of the RPM, so that it can reduce the gas influx flow rate. So it does this until gas influx flow rate gets less than a specific limit. When it happens, it switches the control variable from surface to the downhole and puts the downhole pressure as a new set point, as a new control variable. And at the same time, the new reservoir pore pressure can be estimated. And therefore, when everything comes back to normal and kick is attenuated, we go back to the normal drilling with the downhole pressure having a new set point based on the new reservoir pressure value. So now, as I mentioned before, we design a controller in 3 steps. The first one is a single pressure controller, and the second one is a comprehensive controller, and the third one is a multivariate controller. So in this section I'm gonna present you the results for single pressure controller. And I just I'm not gonna show you the graphs for the results of this normal drilling condition, just because of lack of the time. But the design controller was able to accurate the estimator moving horizon estimator for the single pressure controller was able to accurately determine the friction factor and angular density within 1.5% of actual value in 30 seconds. And also drill bit pressure, controller was able to control drill bit pressure within 72% of set point within 30 seconds. So during connection procedure, okay, first, what is a connection procedure? During connection, we call connection procedure for a time that a new drill pipe is added to the drill string, and in this case the main pump gets ramped down until it gets shut down, and the new pipe is added, and it again gets ramped up, everything back to the normal. But in this condition, we are losing the head of the main pump at the downhole area. Therefore, our pressure at the downhole decreases. So it's kind of dangerous, because if the pressure gets too much lower than the reservoir pressure, it can induce the kick. So the controller that we designed was able to change the chuck valve opening and also the back pressure flow rate accordingly, so that it is able to hold the pressure almost constant within 1% of margin error during connection procedure. And also we found out that this controllers is successfully able to attenuate the kick. So in this graph you can see the controller reaction to the kicks with different cycle time. As you can see, as the cycle time decrease, the controller is able to attenuate the kick faster. The lower the cycle time means we have higher data transmission speed, and this also shows the effect of having a high-speed communication system during the relay. So this graph shows that immediate action avoids more intrusive well control efforts. So in this slide, I'm gonna compare the estimator and the controller in case of corrupted data versus the clean data. As you can see on the graphs on the top, we have clean data, and there is not a specific difference between the L1 norm and the square error. But when we go to corrupted data that they have drift, they have outlier, you can see that L1 norm is able to be more resistive to that. And the same thing again for the controller. In case of the corrupted data, square error has some problems with oscillation, but L1 norm is much more smooth, just the effects that we were expecting to see. Okay, the next part is managed pressure drilling automation with comprehensive controller. So the comprehensive controller was designed based on the models that and the ideas that I just told you, and the results show that ROP, rate of penetration, in case of comprehensive controller increases versus the single pressure controller. And the reason for that is that during comprehensive controller we have less downhole pressure, and decreased downhole pressure exponentially increases the ROP. And also another very great result is the kick attenuation. It was found out that having a comprehensive controller, we are able to even attenuate the kick much more faster. So in this graph, the black line shows how an operator would react to a kick. So it's a manual attenuation of the kick. The blue line shows how our single pressure controller reacts to a kick, and the red line shows how comprehensive controller is able to react to the kick. And the reason it is able to attenuate it faster is because it has an extra manipulated variable, which is the rotation speed of the drill string, and it increases that, and with that it increases the pressure loss in the annulus, and therefore the pressure in the annulus increases, and that avoids more gas influx to come inside the annulus. And another great feature, so like these all of these are new things in the upstream industry that has never been done before. So the another interesting result is that the controller is also, so for example, before that I want to mention you how the manipulated variables change. So the choke valve opening decreased during the kick. The controller also increased the pump flow rate, and as you can see, it also increases the rotation speed. But the another interesting feature for this controller, comprehensive controller, because it considers the interaction between the drill string and the hydraulic, it is able to even hold the rate of penetration consistent during kick. Because whenever it sees, okay, the rotation speed is going up, then it decreases the weight on the bead, so we have consistent rate of penetration, and this consistent rate of penetration avoids cuttings buildup, which is a big issue in the upstream industry. And in the last section, I'm gonna talk about the managed pressure drilling automation with having comprehensive controller with multiple pressure sensors. So in this slide, the left one, you can see the different values for the densities. So remember I told you in multivariate controller we have multiple sensors along the annulus. Because we have multiple sensors, we are able to estimate multiple densities along the annulus. Therefore, whenever there is a cutting buildup in one location, the density in that location gets increased. So these are the results from our moving horizon estimator. So whenever the density is increased, for example in this graph you can see the density at the location 5 starts to increase after 30 seconds. So we can see that, okay, there's a cutting buildup that is happening, and this is and the change in the density is also fed to the controller. so that the controller can do required actions. But in graphs on the right side shows the effect of the cutting buildup on the pressure loss. As you can see, it has it caused very slight increase in the pressure values. That's very hard for the human eye to detect. So this shows the significance of this control system. With this, we are able to detect the cutting buildup much faster, so that the required action can be done faster with the operator. So again, we also tested that with in case of the kick, which happens in not exactly at the beat, at another like location which is more on top of that. So the results from the multiple sensor controller showed that it is able to even have better improved kick attenuation. That's because the sensors that are closer to the kick location are able to sense it earlier, therefore controller can react earlier. And the same thing, this compressor controller changes RPM, pump flow rate, and the chuck valve opening to do this. Graph on the right also shows the clear benefit in not having too much of interruption time. So as you can see, this is again the controller reacting to to a kick with different interruption time. So as you can see, as the interruption time increases for the communication of the data to the controller, it becomes harder for the controller to attenuate the kick. But in all of these cases, the automatic model-based controller is able to reject significant effects of unexpected gas influxes. So in the end, the contributions of this project, we showed that combining advanced high-speed sensing and communication systems with advanced controller can lead to significant improvement in upstream industry, and including managed pressure drilling and TLP platform. So specifically, we designed a comprehensive controller that simultaneously controls rate of penetration and downhole pressure using wire drill pipe technology. And for this, for the first time, we added the effect of drill string rotation on pressure loss in the angulus to the control system. And we also proposed a new and improved method for kick attenuation. And the multivariate controller that we designed is able to faster detect the cutting buildup, and therefore, and it also has better kick attenuation feature. And in case of the TLP tension leg platform, we designed an advanced post-sensor monitoring system based on fiber optic sensors for the first time, and we designed an MPC controller to balance the TLP using ballast tanks again for the first time. The conclusion is again a combination of high-speed sensing and the advanced controller. In case of the TLP platforms, we say that it can lead to very stable transforms and improve safety and economic in that. And in case of the drilling, it leads to synchronized control moves and with enhanced safety and economics that is caused because of higher ROP, regulated borehole pressure, fewer halts in operation, and successfully attenuating the kick. So for future work, all of the simulation that we did, we use a lower order model of the system for the simulation of the system itself, both for TLP and managed pressure drilling. So it's better to use a high fidelity simulator for MPD control, so that we can also test the controller against that, and we can even improve the controller design. And it's also better to design a controller against the 6 degree of freedom model for TLP simulation, just like what it is being done for the UAVs. So another thing is that we can add tendon length changing system as another manipulate variable to the MPC. So for the drilling automation, another thing that can be done is the data reconciliation and validation for drilling. That's because all of the we can design a controller which is able to resist more against data quality problems. So whenever a measurement of a sensor gets lost, so it can use the estimated value instead of that. And also, the controller that we designed this work uses the downhole pressure value to determine the kick mostly. So in future we can consider all the variable changes during a kick event, so that can lead to reduce false alarms during any disturbances during drilling. So publications, I have had 2 accepted publication journal articles, 2 submitted journal articles, and I have had 7 peer-reviewed papers for conferences and 4 proceedings and 1 press release. And in the end, thank you for your attention. I'm ready to answer any questions.